we'll get started this week. Thank you all for coming out to DLS. Again, this week, it's my pleasure to introduce Dr. Brian Merman, Professor of Geosciences at Virginia Tech. That's for a few days. Prior to joining the faculty at Tech, Brian was a research scientist in Chevron's Continental group and other research groups at Chevron. He earned his PhD at Stanford University, a master's at Colorado School of Mines, and a BA at SUNY upstate New York.
Buffalo.
Oh, yes, SUNY Buffalo. Sorry. I have a lot of SUNY genetics. Brian is a sedimentary geologist, marine geologist, paleoceanographer, and interested in reconstructing tectonic, climate, and fundamental sedimentary processes to a stratigraphic record. He's accomplished more than 15 years of outcrop characterization, often in rugged mountainous regions of Estonia, and 3 international ocean discovery program expeditions. I was actually on his first IODP expedition at the first cross paths. Brian's well known for his expertise in deep water sedimentary systems like turbidite, chondrite sediment drifts, source to sink signal propagation and processes, and recently marine sedimentary archives of ice sheet dynamics. Probably combining a lot of these things. Brian was an IODP Distinguished Lecturer from 2018 to 2019. He's also been recognized with the James Wilson Award for Excellence in Sedimentary Geology by an early career scientist by the Society for Sedimentary. On the really important service front, Brian has served on the Science Evaluation Panel for IODP. So IODP votes is a really important panel for getting proposals through an expedition started. He's a co-author of the 2050 Science Framework for Scientific Ocean Drilling. Looking forward to look at that. And he's been the lead and been involved in many industry research for help support graduates. During his early industry, professor days, he wrote the science blog Classic Wired magazine. Don't know about that blog? I sent your how to apply to grad school is a post that I send people. It's also my opinion that Brian has a great sense of humor, a great taste in music. And in a recent conversation, we were like, well, if you wasn't a scientist, what would you be? Okay. Or would you book artists for the venue? We're very happy to have Brian joining us here this week and today. So take it away.
Thanks, Pete. All right, thanks for having me. I visited here many years ago, but I love coming to this department, to this building, this area. So thanks for the nice welcome. Look forward to the rest of the day. I like the seminar being in the middle of the day instead of the end. I think we might need to do it that way. So Pete gave a nice introduction of kind of the context of where I'm coming from. And I'm going to, again, I'm a sedimentologist. I'm not or at least my background's not paleoclimate, paleoceanography. I've sort of gotten into that realm of study through sedimentology stratigraphy. So my background is, see if this works. It does not. Okay, there we go. There we go. My background is really field geology, and I still do field geology, but maybe not as much as I did in both master's and PhD. In the early part of being a professor, I've done a lot of field work looking at not solely, but mostly deep marine clastic sedimentary systems, but also some shallow marine and a little bit of non-marine here and there. But kind of coming from this world of outcrops and field work, that's a much younger me, but I think I can still get up on these mountains, no problem. So that was my tool, so to speak, of studying sedimentary deposits and their processes. And then I got into using this tool, right? So instead of going out to ancient sediments now uplifted into mountains, but using coring and scientific drilling to access the sedimentary record. And I've been fortunate enough to go on 3 IUDP expeditions starting in 2012, which Pete was on as a postdoc, picture postdoc, Pete. And then two others. I'll talk about the two others in this talk focused on high latitude settings, so both Antarctica and the Arctic. But before I get into that, and again, you can get a lot of information out of these cores, of course. You all know that, right? You can make lots of measurements about the chemistry, about the paleobiology, combining those. And again, I'm coming from what can we get out of these cores about the physical processes, about how the sediment got there, which in some cases is a proxy, but in other cases is also the context for all the other information. But before I get into that, I just want to talk about, kind of set the big picture here and kind of the importance. I don't need to tell you all this as geologists, but the importance of studying history in the broadest sense. And I really like this kind of essay from, I guess, 8 years ago now, talking about, why study past climates, right? And again, I think you all appreciate this, but I think this essay does a nice kind of job talking about this, of what ancient climates provide us, right? Allow us to potentially test the climate models on which future projections are based. We can explore the impacts of climate change on ecosystems and interconnected Earth system processes, right? So past Earth has kind of done these experiments, so to speak. So what happened? What happened to life? What happened to the environment? What happened to the Earth system? You can explore that with models as well. So it's not to say, we don't do both, but this is an important way to investigate. And then identify important processes that, maybe have not been incorporated into our current understanding or certainly our models. And I also like, this quote, Earth history has an even deeper role to play in the modern conversation and public understanding of climate change. It helps us comprehend and narrate what might happen in a warmer climate. So the kind of title of this, Climate Change Narratives, or stories, if you like. Yes, getting the numbers and the quantitative constraints and the thresholds of these processes is all very important. But there's also, stories in the past that I think we could, sort of emphasize or highlight when we have conversations with the public about Earth system change. And then, of course, studying history, these go together, hand in hand, is the context. And this is the very first figure in the latest IPCC report, at least in the component called Physical Understanding of Climate. I can't remember the exact name. But the very first figure in this gigantic report is setting the context, right? That Earth's climate system has evolved over many millions of years. Evidence from Natural Archive provides long-term perspective on observed changes, right? So again, as geoscientists, geologists, you are already in this mindset, but sort of the rest of humanity, of the public, does not think in these multiple timescales that we naturally do. But there's a lot of value in that. And so, like many of the big challenges facing humanity, historical context provides important insight. You've probably all heard that. For any given problem, social, economic, political, it's like, well, let's look at the historical context. That's an important basis for taking things further. So again, this kind of set up, again, talking to this audience, you're kind of already with me, but I just wanted to take a few moments before I get into those details. I did not learn my skills as a sedimentologist, stratigrapher, thinking about sedimentation and under the influence of ice. So this is a little newer to me, but I like learning new things. And so my current focus to the grad students in my group, we're focused on glacial marine sedimentology. So the sediment transport and deposition that occurs near ice or, out in front of ice sheets. And the big motivation, like why did we spend all this time and resources and money to drill these sediment cores near these ice sheets? Why do we care about past ice sheet behavior? And as you all know, right, the potential destabilization of these large ice sheets is one of the biggest among, the handful of very big potential Earth system changes that we're worried about. And so, the need for paleoclimate records that document ice sheet response to a range of forcings. So not only past warm periods, although those are clearly critical, but, the full range of climatic forcings and change, and sort of learning how these ice sheets respond to that change. So I'm going to talk about, in a broad sense, the West Antarctic ice sheet, Antarctic ice sheet, and then Greenland will be maybe less so of this talk because that's newer research. We'll see how far I get. I'll first try to, communicate, convince you that the continental slope sedimentary record is a very important archive. It does have sort of some challenges and complexities that I'm going to get into, but also has some advantages and some value that I think is unique. And then most of the talk will be about our work looking at a sedimentary archive that we link to Antarctic bottom water. So it'll be a little bit of oceanography. And then this expedition, this was 2018, this was 2 years ago. So some preliminary results and ideas from the Greenland work. And then some concluding thoughts. There's the JR in 2018 getting an escort through the sea ice by the Palmer, which is an icebreaker in the JR. I now have to say the JR was not, because the JR is retired and in cold stack, which I think just means it's sitting in the water, never to be used again, probably turning into scrap sometime soon, sadly, but it had a good life. All right, continental slope. So just really simple cartoon here, cross section of an ice sheet, kind of, land would be off to the right, the continental shelf, and then down into the deeper water, the continental slope. And so why are continental slope records, sedimentary records, important? And really mainly the thing to think about here is that these deposits are preserved during all the back and forth of the ice sheet, right? The shelf deposits are extremely valuable. There's people that focus entire careers on looking at the shelf deposits since the last glacial maximum that are left behind, the morphology and the archives. But as you all know, with the back and forth, especially over the last couple million years, right, a glacial maximum might look something like this, with the ice sheet extending out to the outer shelf or even the shelf edge, helping build this shelf, in fact. And that back and forth really, at a best, modifies this, at worst, completely destroys the shelf record, right, through all of that back and forth. And this, of course, is the past 3 million years oxygen isotope record, just to illustrate the many dozens of advances and retreats across the shelf. And the continental slope sort of too deep, right? It's sort of protected from that. So that's kind of a takeaway. It's like why the continental slope is an important archive. And just a few things from the literature. This is a book from 1990 that, again, I'm pretty new to glacial marine sedimentology, so digging into some of this seminal literature has been really interesting and fun. But this quote, "A problem with the modern record is that some glacial marine settings that are relatively common in the past are scarcely represented at present, or current state, or the last few millennia, of course. For example, the presence of grounded glacier ice to the edge of continental shelves. We don't see that condition today." And a newer paper by John Yeager, Michelle Copps from several years ago, stating the most complete stratigraphic record of glacial interglacial ice dynamics is found beyond the continental shelf break. So that's where we're going, why we're focused on the continental slope. So what are these slope deposits? I've colored yellow here in this cartoon. What processes lead to their accumulation? How do they relate to ice sheet dynamics and in turn climate forcings? And I feel like when you study paleoclimate and proxies, you inevitably end up studying how the proxy works, right? And that goes the same for geochemistry, but in this case, sort of physical proxies. Like how are these records constructed? And how does that influence how we might interpret them? There's a lot of processes happening on glaciated margins. This is from a relatively recent paper showing some of them, right, with the ice sheet at the shelf edge, and it hosts deposits of various, types, downslope sediment gravity flows, ice rafting, right, debris embedded in ice, the ice melts. Meltwater plumes are a very interesting one. Of course, background, fine-grained sediment settling. Oceanographic currents, as you'll see, can be important as well. And for this talk, I'm going to focus on what are called channel levee systems. So these submarine channels that form and they build their own levees, right, that help keep them confined through this natural process. And if you're not familiar with turbidity currents, this is just a nice video of a flume tank little experiment just to help you visualize. But turbidity currents are these mixtures of sediment and water. The suspended sediment essentially increases the density. It's a density current, and it flows under the force of gravity, right? So we call them sediment gravity flows. Turbidity currents are a type of those, and the deposits from those are called turbidites. And, as one of these turbidity currents comes down this sort of channel on the seafloor, what happens is the top part of the flow up here ends up spilling out of the channel, and it constructs these levees, these overbank levees through that process, which further help confine it. A really interesting kind of morphodynamic feedback. And so a simple cross section, so this of a grading, accumulating channel levee system. The channel would be here. And you could just kind of picture the flow that goes through the channel is more concentrated, more suspended sediment concentration. It's coarser, and up in the flow that spills out is finer grained. So we get sort of a coarse grained axis and then a finer grained levee. And these are known from around the world, have been studied for a long time for different reasons. Question here, why are these deposits a suitable target for proxy archives? And both these expeditions I went on targeted levees on purpose. Some advantages, little to no erosion, meaning there's a high degree of stratigraphic completeness out in the levee, certainly compared to the channel, which can have a lot of erosion and reworking, more complex stratigraphy. And we also have evidence of other processes preserved. Another reason why paleoceanographers, paleoclimate folks like these records is that they offer an opportunity for very high temporal resolution because they accumulate quite fast. Certainly compared to, say, open ocean, deep ocean pelagic records, maybe tens of centimeter or more per 1,000 year, right? So if you're interested in the resolution, like you're interested in millennial or suborbital or whatever the temporal resolution is, your archive, of course, needs to capture that. And there's an inherent linkage to the shelf processes because that's where these flows come from. But any archive or any proxy doesn't come with its challenges. In this case, we'll just sort of say the local processes might obscure some of the broader signal of interest. Right? So you end up studying the processes that built the stratigraphy rather than the bigger signal. So that's something to keep in mind. The physical processes could overwhelm sort of the paleobiologic and or geochemical signals. And in some cases, there's a lack of abundant datable material right? To do climate history, you need time. So there can be some challenges in an archive like this that they're not unsurmountable, but they need to be considered. Okay, so I'm going to talk about Antarctica. I really want to highlight that this work really comes from a former student of mine, Natalia Varela, who's currently doing a postdoc up the road from us at University of Virginia. I was hoping this paper was going to be officially accepted by this talk. It's like any day now. So most of this talk is going to kind of share, this was a big chunk of Natalia's PhD. This reference doesn't get a citation. You're going to have to look it up if you don't know it. But there is water at the bottom of the ocean. Under the water, carry the water. So if you're not familiar with Antarctic bottom water, also this map on the right might have a projection that you're not familiar with. It's really ocean-centric map projection. And Antarctic bottom water is just what it sounds like. It's the part of oceanographic sort of stratification, if you like, that is at the bottom, and it's sourced from Antarctica. Antarctic bottom water is a globally important water mass in terms of helping store carbon in the deep ocean, right? In addition to many other processes that oceanographers study Antarctic bottom water that sort of gets into the global ocean. It's an important part of the modern physical oceanographic setup. And the Ross Sea, where I'm going to take you, this big embayment here, is one of the larger contributors of where Antarctic bottom water is sourced. There are others, like the Weddell Sea. This simulation, the sort of tracer simulations highlighting the Ross Sea. And all to take from this is sort of seeing how this dense, cold water gets far from Antarctica, sort of influences certainly the Southern Ocean and even the global ocean. And so the Ross Sea is a large, here's the Ross Sea, a large contributor. And in short, I won't get into all the details of how this process works, but in short, Antarctic bottom water is formed as what are called polynyas, these open where you get sea ice and the winds push the sea ice. Sea ice keeps forming. As sea ice forms, the leftover water, so to speak, is now denser, right? And so it sinks and calls what's called dense shelf water. So the best way to think about this is actually this video from the Australian oceanographic community. It's a really nice video that I'll just play a part of this just to help you kind of think about this. The video first is going to show sea surface temperature, so cool colors are cooler, and it's showing sort of a seasonal cycle here through the spring, summer, and autumn, and you can see the sea ice layer contract and expand in accordance with the seasons. And then this visualization is going to strip off this layer. Well, first it's showing now the current speed. Now it's stripping off the surface ocean and just focusing on the bottom water. It's basically simulating sort of the densest part of the water. So here's the Antarctic Peninsula, and there's this dense water on the shelf that basically spills off the continental shelf. And now you can see it in this visualization kind of making its way into the South Atlantic in this case. Next, this visualization will pan over to the Ross Sea, where we'll spend the next 15 minutes or so thinking about. And again, it's showing the surface current, what's called the Antarctic Circumpolar Current, now stripping away the surface. And again, this dense water, and I want you to really focus here. And it's really showing this, what's called dense shelf water that's cascading off the shelf edge, right? Because it's denser, it's finding the bottom. And these are really important contributors, at least certainly in the modern, to where Antarctic bottom water is formed. And again, this process is winds sort of push the sea ice offshore, You get these open water areas called polynya, then sea ice forms again. So it's this very continuous process leading to this dense shelf water. And this dense shelf water, just as it sounds, can then kind of make its way across the shelf and then into the Southern Ocean. One particular mode of this is that some of this dense shelf water gets funneled into submarine canyons, and then it is vigorous enough to then pick up sediment. All right, so we're going to focus on that, the density currents that come from dense shelf water that then make their way down these submarine canyons. So this cascading can then entrain sediment, and now these density currents can evolve into a type of turbidity current. Very low concentration, still driven by dense water, but now they're carrying sediment, which means now we have a record. Right? Whenever there's sediment carried and deposited, now we can go interrogate that record. So that's kind of the big setup for how all of this works. The record I'm going to show you certainly doesn't represent all Antarctic bottom water history, but of this particular mode. So that's important. This is what's called Hillary Canyon in the Ross Sea. And I just want you to sort of think about the scale of this. So this would be coming out at you, right? So this is the canyon, the channel. It's about 40 kilometers from the crest of the levee to the other crest and almost 500 meters deep. So this very gigantic conduit, right? Much bigger than, quote, normal submarine channel levee systems. And that has a lot to do with the dense water context here. And we drilled a site, U1524, right at the crest of this levee to, among other things, capture the record of this process. So this was the target and the design of this from the get-go. Right, so that's kind of this idea in this cartoon that these sediment-laden currents come down this channel and then they spill sediment out, helping build this levee over time. It's a little bit of a complicated map, but just to give you context, here's the Ross Ice Shelf. The continental shelf in the dark blue would be the deeper ocean. And so Hillary Canyon sits, at the shelf edge and down into the continental slope. And we're going to look at two sites. Two sites were drilled on the flank of this, sort of help constrain these processes. I should say this expedition, 374, drilled some other sites on the shelf that I won't have time to get into, but some interesting paleoclimate records there as well. So here's a simple kind of summary of this record. It's about 300 meters deep, thick. These are the age datums, just to give you a sense, 3.32 million, in case you can't see that in the back. And, this mostly very fine-grained, diatom ooze, right? Diatoms love the Southern Ocean. That would be the yellow, mixed with terrigenous, mud and silt. And what we focused on were these very distinct and discrete little layers that were millimeter scale in thickness. So this is centimeters here, that have a sharp basal contact. Again, they're usually a couple millimeters or a little bit more thick. Often this little different color. And even visually, you can sort of tell slightly coarser material than the background. So we focused on these, which we interpreted as the deposits, these sediment gravity flow events. In this case, the larger events that are kind of standing out from the background. And we did a very sophisticated analysis of counting them. So Natalia counted a little over 3,300 of them. So that's what's the horizontal lines here. And then the blue ones are ones we sampled, sort of representative sampling to look at the grain size. Again, in terms of thickness, pretty consistent thickness, millimeter and a half, maybe 2 millimeters. Really no stratigraphic pattern there. In terms of grain size, we're looking at a median, sort of in the fine to medium silt, the 90th percentile. Some of them get up into very fine sand. So certainly not very coarse, but coarser than the sort of background sediment that they're sitting in. Either thickness or grain size, there's no systematic, significant stratigraphic pattern or trend. Kind of are pretty consistent through the succession. So we focused the analysis on looking at their relative timing and their frequency, since the processes were relatively consistent through time. So what about the timing and frequency of these turbidity current events? I'm going to skip this. That was just a little video for fun. So we kind of, I'll walk you through this visualization. We're using what we just kind of ended up nicknaming the barcode plot, you know, the thing you scan at the grocery store. The barcode, again, each horizontal black line would be a single one of these, the position of a single one of these 3,300 events. And that's for this site U1524. And we assigned ages to these with what's a relatively good age model. The chronology coming from the biostratigraphic and paleomagnetic age control. We did the same for the other site, 1525, which is more proximal. Sadly, it didn't go deeper, so it's just the base of the core, not the that it lacks all those deposits. So we're able to compare these two sites that are in the same overall system, which I guess as a sedimentologist is very important to do because you can get local processes and dynamics in any given spot that could, not represent the broader signal that you're interested in. So again, I won't show it due to time, but the grain size and thickness data for this other site is very similar in the sense that there's no stratigraphic trends or patterns. So again, we're going to look at basically the timing, when these events occurred and their frequency, their clustering, and so on. I know you can't see these, but this is the age control. These little colored lines are the age datums, just to kind of show you that. Then what we did, just because it can be hard to see when they're very clustered in time, like how many events are in there. This is just a density curve overlaid on that, so you can sort of see where the peaks are going to the right, or times of more of these events happening, so a higher frequency of these events. So you can kind of look at that and start to, geologists are really good at finding patterns, sometimes when they might not exist. But just sort of a visual kind of display here. And what we do in the study is sort of relate this to this process and interpret these as being linked to this dense shelf water cascading process. And so, strong outflow, except for this notable gap I'll talk about, this kind of overall diminishing. Then we get into this high amount of variability in this about 1 million years ago, and then kind of this shutdown later. And so I'm not going to talk about all of these in this talk, but sort of give you like the highlight reel of the record. The age control is good, but not so good that, we're trying to get to sort of millennial scales, sort of a bigger picture story here. This is the famous oxygen isotope curve, just for context, sort of kind of see the overall cooling through 3 million years and the change in the kind of frequency of the fluctuations, just to give you a sense of where we are. So we emphasize the interaction of multiple controls. There's the sea ice polynya formation. Importantly, there's the amount of continental shelf area, right? Because this dense shelf water, for this process to occur, there need to be sufficient shelf area. And then the influence of other currents sort of impacting this physical record. So first, the latest Pliocene. And the late Pliocene part of the record is a time of overall cooling, especially relative to the early and mid Pliocene. And there's other proxy records from Andrill and other sites that support this, that there's ice sheet growth during the late Pliocene and with that sea ice polynya formation. At the same time, there was sufficient shelf area for this dense shelf water process to occur. Because the ice sheet was not as large and as extensive as it would become in parts of the Pleistocene, especially the later Pleistocene, again, there was sufficient continental shelf area. We then see, kind of a diminishing, weakening into the early Pleistocene that we interpret reflect an expanding ice sheet, less continental shelf area. But then we see this time period known as the mid-Pleistocene transition. Maybe some of you even study this time period. Very interesting time period that people still vigorously argue about. In our record, we see a lot of variability. We see both sites sort of increase in these events overall. Both sites abruptly stop. So this is sort of both sites a lack of these events. And then resume, but only in one site. So there's sort of a lot of variability happening in this 1.2 to kind of 0.7 million year ago, this mid-Pleistocene transition. So I'll come to these gaps here in a second, but the latter part of this record, or the upper part of this record, where these events come back in this proximal site and at their highest frequency, but then they don't at this more distal site. And how we interpret this, and this is supported by a lot of really good seismic stratigraphic mapping and other studies of this area, is that what's known as the Antarctic slope current, this long slope current, really kicks in around the mid-Pleistocene transition, and it's positioned sort of in between these two sites. So we sort of interpret that this current kind of influenced the preservation of the sediment, potentially sort of pirating that sediment, preventing it from depositing down dip. And so that's kind of a interesting complication, right? That, well, the dense water was still happening, but this particular site didn't record it because of another process, which is obviously another challenge when kind of using these kinds of records. So the two sites were critical there. Otherwise, that's difficult to detect. And then we have these notable gaps. There's one down here in the latest Pliocene, or the late Pliocene, and then this one here, where this, in an otherwise high frequency deposition, we see these cessation of these events. And they're well constrained by the chronology, at least well enough to make an interpretation that, we suggest that these are linked to these so-called super interglacials. KM3, if not that exact one, there are some interglacials in this time period here that, based on other data, other proxies, geochemistry and fauna, interpreted to be when the ice sheet collapsed or at least retreated very significantly during a anomalously warm interglacial. And marine isotopes stage 31 is another one of these that people are interested in, that have been nicknamed super interglacials. So we're suggesting that we're seeing sort of this collapse. If you don't like the word collapse, it's kind of aggressive, but this significant retreat of the ice sheet, warming. So sea ice is potentially not even happening, right? So this engine of dense shelf water is not occurring during these times. So to summarize that part, right, the timing and frequency and the characteristics of these millimeter scale deposits we use to reveal part of the history of this one important mode of Antarctic bottom water outflow and history. And so it's hard to show how this gets integrated with other proxies in a single talk, but that's the next step with our collaborators. How does this relate to the ice rafted debris record, to the biogenic opal geochemistry, to the sea ice proxies that people work on and are developing? And that's where we are now in this kind of multi-proxy approach, and us coming from this physical sedimentology world. I'm going to kind of blast through Greenland a bit because I want to leave time for questions, but this is newer. This expedition was just 2 years ago. So this is more some ideas just to share. Also levee turbidites, but as you'll see, quite different. So this expedition went to northern part of what's known as Baffin Bay, offshore of the northwestern segment of the Greenland ice sheet. In this map here, so the Canadian Arctic Islands here, Greenland here, Baffin Bay, and we targeted one of these, what's known as a trough mouth fan. It's basically this, large sediment deposit that forms through the process of ice sheet advance retreat over time, basically building out. You can see this kind of shape like this, like protubing out, like building this shelf out with the glacial sediment over time. So again, anytime there's a pile of sediment, sedimentologists will go look at it and see what history can we get from that. And so this expedition, we drilled 6 sites, and I'm going to focus on these slope sites. So again, this is the shelf. Here's the coast here, deep water out in the purple. And so this seismic reflection profile shows that shelf edge to slope. We drilled some shelf sites as well. If you're interested, I can tell you about them. But we focused on these 2 companion sites that are down on the continental slope here that capture the last million years, especially the kind of mid to late Pleistocene. Zooming in on that, you can see different characteristics than the gigantic Hillary Canyon. These are smaller. This is a 5-kilometer bar here, but we drilled a couple sites in this overall channel levee depositional system. So again, targeted by design to go for these relatively complete and high accumulation rate successions. Also, like Expedition 374, drilled near the crest of the levee adjacent to the channel. So this kind of idea, right, of capturing the sediment that spills out of that channel and is, again, relatively complete record. So what do these, sediments look like? Again, here's a 240-meter thick, really simplified lithologic column here. In this case, very little biogenic sediments, very much coming from land, and as you'll see, quite a mixture of deposits. We have much coarser grained material. Here's a photograph, an X-ray, and then a line drawing. Some different facies, some sort of thicker sand beds, some coarser sand beds, some of these outsized clasts sort of sitting within or sometimes clustered. So lots of different deposits and processes here, but these thin yellow layers that we interpret as turbidites, again, are the focus. So we did a similar approach at first, and this is quite new data. Here there's 7,200, almost 7,300 of these layers in our kind of barcode plot, and again with just a density curve to maybe help see the patterns there. So this is very new. I need to shout out Faison, PhD student, doing the hard work that every dissertation or master's project has some tedious task. You just can't escape it. It's just part of it. This is Faison's. It's counting these layers with the core images. So a very interesting record that we're now kind of getting into. What do these patterns mean? What can we learn from this record? And so to set up some hypotheses, and these go back, decades in glacial marine sedimentology, of a scenario like this, where during glacial max, right, you have your grounded ice sheet at the shelf edge, and basically that essentially stages sediment at the shelf edge, pushes it down, right, and that's how you trigger turbidity currents, right, and so this shelf to slope transfer is sort of turned on during glacial max. And then during deglacial, so the ice sheet's retreating, right? You get other processes like ice rafted debris, that's what IRD is, some of these meltwater plumes, and the turbidity currents are not active. And that model, conceptual model, comes from Antarctica and, you know, has been interpreted for different systems. Another scenario is pretty much the same idea for glacial max, but then also turbidity currents triggered by the abundant meltwater during the early deglacial especially. And this comes from studies more in the Arctic, sort of northern hemisphere. And so this is turbidites are happening kind of anytime. And then there's kind of another model that has turbidites only during meltwater. So we're sort of faced with, well, we can't just go in here and say interglacial, 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 right? So these are the hypotheses that have been in the literature that we're hoping to test with this pretty one-of-a-kind, really high-resolution record. So the next steps are to do things like characterize what's interpreted as the ice-rafted debris and whether or not it co-occurs with the turbidites, sort of help define these different conceptual models. It's important because you can't just go into this record and count the marine isotope stages like you might in an oxygen isotope record. It's telling us something about this particular part of the ice sheet, this particular ice stream. So we're not really looking for a global record. We kind of know that, right? We're looking what happened to the ice sheet here, right? So looking at a more regional or sort of more specific questions. And just like the other study, to help minimize influences of local processes that might be unique to that site, there's a companion site in the same overall depositional system with some differences that we think will help sort of put that full story together with those two companion records. All right, so heading home. This talk is heading home. This was somewhere in the North Atlantic, a couple days from Iceland on the way home. And we had like 4 days of this kind of sea. The first few hours was kind of fun. And then we were like, okay, I want it to end. Thankfully, I don't get seasick, but I was feeling it during this. Thankfully, in Baffin Bay, it was nice and quiet. It was good for drilling, but this was on the way home. So some concluding thoughts based on this work. Antarctica, as has been known for a long time, is that what's called oceanic forcings, the role of oceanic currents and water masses in this ice sheet are very important, this dense shelf water being one of those. This specific mode of Antarctic bottom water production was studied, highlighting these interacting controls of climate, polynya formation, for example, but also the context of the system, the shelf area, and these other currents. Potentially seeing the sort of shutdown of this process during these super interglacials. Greenland, ocean currents do impact this system, but they're much less dominant than Antarctic systems. We don't see this dense shelf water, at least in Western Greenland. The channel levee deposits, I should have mentioned, really high accumulation rates. We're looking at suborbital or even maybe millennial records. So are we looking at sort of dynamics of advance and retreat that are not captured in our simple models of back and forth, right? Some pulses advancing during an overall retreat. Are we seeing those? And ice sheet modelers are really interested in these records to help think about that. And just what is the expression of advanced retreat on the slope? And again, the physical record provides this foundation for other proxies. So the slope records are complete, right? In the sense they weren't destroyed as the shelf records were, but they also have some complexity we need to figure out. Right? How were they constructed? How were they built? Right? And importantly, what does the slope record tell us about ice sheet dynamics we just can't observe today, and maybe we aren't capturing in our models quite correctly. So a lot of these projects have ice sheet modelers sail on them and are involved in the science So they really want to get information from these kinds of studies to help give them insight to improving the models and vice versa. So it's a really interesting interdisciplinary way to do it. I'll end here. These photos were taken basically a minute apart, looking off the port side and then looking off the starboard side in Baffin Bay. Thanks. With that, I'll take any questions.
Right at the beginning, dense bottom water being formed by
Yeah.
when you showed that bottom water flow, lock up in the pipe, it's very opposite. Summer when it's open, less dense water, and later on, the second part of the salt water.
Yes. So for the dense shelf water, yeah, when you look at the physical oceanographic literature about this process, it's called brine rejection. So you're densifying the water, right? That from the sea ice formation, that does form seasonally, but that dense shelf water accumulates on the shelf over years to decades. And so it doesn't all flow off immediately. That visualization from that movie is probably trying to show longer time scales, sort of decades or longer. So you don't really see that cascading at a very distinct seasonal rhythm. I should say that's difficult to constrain and study. People have put current meters and things at the heads of these canyons to try to capture these processes, but there's not a lot of data of direct observation of them. I don't know if that helps with the dense water question. Well, the sea ice formation can be seasonal, but the dense shelf water then accumulates on the shelf such that you get enough that it starts to then move basinward.
Second part, why would meltwater be driving? Why would that hypothesis?
Yep. So the meltwater idea is, sorry, let me find that, is not so much about the water mass itself, but being that vigorous meltwater processes are basically delivering a lot of sediment to the shelf edge, where it can then, so you're building these kind of what's sometimes called grounding line fans, or these basically deposits out in front of that or from a lot of vigorous meltwater, whereas there's maybe not a lot happening here. It's pretty static, right? And those deposits are then perched sort of at the shelf edge where they then can feed turbidity currents. So it's a little bit more of a 1-2 step process rather than a direct. This system, at least this part of Baffin Bay, there isn't this dense shelf water phenomenon happening. It's a very Antarctic thing because there's really not the same kind of sea ice formation at the same scale, at least on this side of Greenland. There is some dense shelf water processes in East Greenland, but they're not to the scale of the Antarctic systems. They have these huge shelves that accumulate a lot of this dense water over time. Hopefully that helps. Gabe?
I was thinking a little bit about the continental.
Yeah, that's a good observation, right? Like if you were to just sort of count these up and take the age model at face value, these are happening at sort of centennial scale, right? So I think we're looking at events that are high enough magnitude that we're seeing them expressed in this record as these relatively coarser, thicker events. But sort of the background sediment, I should say, in all of this, if you tally up all of these little silt layers, they're like 1% of the whole record. But the background is laminated like throughout. So there could be events that are happening more frequently, but they're just not high enough magnitude. And we didn't get into it because they're hard to distinguish from other processes. Whereas this is sort of like the highest magnitude events that we can feel confident represent this process. But we're only getting a fraction, I would say, of the events, if that makes sense. Yeah, exactly. For Greenland, it's a little bit more frequent, but there's still, if you do this sort of simple experiment, it's still events that are decades to century sort of recurrence, not, yearly. But I think those are in the record, but they're kind of masked by all the other processes, and I don't feel confident to interpret every single lamination as necessarily a turbidity current. There could be other processes. So it's kind of like we have this filter on our record, and we're just getting the high magnitude ones, and therefore they're not as frequent.
Levees are building up.
Mm-hmm.
So, yeah, I guess.
Right. Like basically you're increasing your levee crest to channel floor relief through time instead of them. Basically you're getting this instead of like in concert. So well, in short, we don't, because we don't have, paleoceanographers do not drill in axes of channels. Like, I think for good reason. As a sedimentologist, I would love to. But we don't even know the caliber of the grain size down there, right? And I didn't get into this talk, but we did some numerical modeling of the turbidity currents with Zoltan Sylvester, suggesting that sort of this scale of feature and the grain size and the thickness of these layers suggest really, really low concentration flows that we're not moving incredibly fast. But it's really because it's the dense water that's like maintaining this. So there may not even be very coarse material in the channel. It doesn't answer your question about relative aggradation. But yeah, if you're sort of cutting off, but since the grain size and thickness does not, I expected them to fine up and thin up, and they don't. I think that would be support for you're seeing sort of a change in relief. And same with Greenland. We don't see any trends stratigraphically in thickness of events or grain size. It's sort of relatively consistent. I guess we've run out of time, but I'm happy to hang around and answer any more questions.